Welcome. So now we're going to be learning about congruence. Right? And this lesson is called Congruence Transformations. This is in your notes. The formal definition is in your notes as well as the congruent symbol. So an informal definition. So first of all, our essential question, what does it mean for two figures to be congruent? Here's our informal definition. It just kind of describes it, right? But it's not one that we could prove. It's a little vague. So it's just to kind of get an idea in your head. Right? So informally, two figures are congruent if they have the same size and shape. Right? So that's a little hard to prove mathematically. You know, if it wasn't so vague, then we could prove it more easily. So a more formal mathematical definition of congruence depends on the notion of rigid motions, right? And that we can use to prove two figures are congruent. So our formal definition, two plane figures are congruent if and only if one can be obtained from the other by rigid motions, that is, by a sequence of reflections, translations, and or rotations. And that's what we were just learning. And there below we have the symbol for congruence. It's an equals with the squiggle. The equals part, so actually let's go over the parts of that just so you know. So this part here means same shape. Technically it means similar. Two figures that are similar have the same shape. Equals means it has the same measure. Right? And that's where that symbol for congruence comes from. Right, so we're going to be looking at congruence transformations. So we're just building upon what you've learned with transformations. And just waiting for the page to turn. And there it goes. All right, so our congruence transformations, the pre-image is, of course, of our original figure. And as the name implies, congruence transformations, our figures are congruents. So we have a translation or a slide, which moves all the points the same direction, same distance in the same direction. Slide is just sort of a description. Translation is the correct name. Let's actually identify that this particular transformation, or excuse me, this particular translation. Right, so now if we look at our, so remember these are our translation vectors. Right, that's what those are. Our vector here is going, so it's going 1, 2, 3, 4, 5 to the right. Plan to face to right. We have write it down here. Translation vector is getting in the way of me writing anymore. 1, 2, 3, 4, 5 to the right, and 2 down. So I'm just going to write here 5 and 2. Right, and this one went to the right, and this one went down. Right, and so in coordinate notation, that would be txy goes to x plus 5, y minus 2. Or we could also write that in vector notation. And then we would use our vector, 5, negative 2. And this is telling us the movement. Right, so the first value tells us to move, since it's positive, it's telling us to move 5 to the right. Since the second value is negative, it's telling us to move 2 down. Now we have our rotation, which turns a figure around a fixed point called the center of rotation. We also need to know the angle of rotation. Here our angle of rotation is drawn in, as well as our point of rotation. So the point of rotation is 0, 0, or the origin. The angle of rotation depends on which direction you want to go. Right? If I go this way, that is 90 degrees counterclockwise. If I prefer to go this way, that would be 270 degrees clockwise. Either way, you end up in the exact same location. Right? So if we're writing our transformation here, we can write, and this is a rotation, 90 degrees counterclockwise, or 270 degrees clockwise about the origin. We also could write this in a type of coordinate notation, right? So remember we had our way of showing how the coordinates are changing. So for a rotation 90 degrees, xy goes to, let's think about how our points are changing, right? So let's take a look. Let's compare. These are two corresponding points, right? So this point here is -1, 1, 2, 3, 4. Oh, and that comma just looks very odd. Let me rewrite that for you. -1, 4. And this is its corresponding point right there, and that's the point 4, 1. Notice that x and y are switched, and that's what's going to happen on a 90-degree rotation or a 270-degree rotation. Notice that the signs are not the same. So they flipped, right? But it's no longer, so when I flip it, it would be 4, -1. It's no longer 4, -1, right? The second one became the opposite. So in this case, a rotation to change our xy to y -x. Right? And we can look and see, they're flipped, and now the second one should have been negative, but it's positive. Right? And then let's look at the last one here. We have a reflection, which flips our figure, our pre-image, our figure over the line called a line of reflection. This particular reflection is a reflection over the x-axis. We can also write this in coordinate notation as well, right? So here it would be our x-axis. And how does that change our points? Notice R for reflect, R for rotate. How can you tell the difference? Well, you don't rotate around the x-axis. How could you ever get around it? It never ends, right? You rotate around a point, you reflect over a line. Right? So reflect over the x-axis, xy becomes, one stays the same, one changes. If you reflect over the x-axis, x stays the same, and y becomes the opposite. I almost ran out of space there. If I move this one over just a teeny bit, I can move this one over just a teeny bit, and then, oops, everybody will fit. Now on the second and third diagrams here, it's a little hard to tell who's the pre-image and who's in the image. But on the first diagram, it's very easy to tell who's the image and who's the pre-image. Right? So the vector goes from the pre-image to the image. Right? The vector shows the movement, and we move from the pre-image to the image. So then we can probably assume that in all the cases here, the blue was the pre-image and the green was the image. But it wasn't going to change the transformation anyhow. It would change it on translation, but it wouldn't change it on a reflection or the rotation. Right? All right, so these are our three types of congruence transformations, and these are the types of transformations that we're going to use to prove two figures are congruent in this particular part of the lesson. This, by the way, was not in your notes. It's not bad to have it in your notes, but this is in your notes. All right, and I have this as a screenshot in your notes, so you have all of it in your notes. I don't think there's anything that's not in your notes. Nope, the entire thing is in your notes. All right, so I'm going to use my handy dandy little arrow here to try to show you where I am. All right, so because I can't point, I can point, but you can't see it. So my arrow is going to point for me. So a transformation in a coordinate plane can be described as a function that maps pre-image points inputs to image points outputs. And that's going to be true whether we're talking about a transformation in geometry, or later on a transformation in algebra 2, or pre-calc, or calculus. So translations, reflections, and rotations all preserve distance and angle measure because for each of these transformations, the pre-image and the image are congruent. Do you remember what we called a transformation where the pre-image and the image was congruent? Let's write that in our notes. This is not in your notes, but I want you to add it. Right? So congruence transformations are isometries. Now I have a little box that you cannot see. However, it is preventing me from writing, and that's why my eye did not appear. There he comes. Are isometries. Right, so isometry, that was the word we had for a transformation, a rigid transformation. Right, so isometries are rigid transformations. They are congruence transformations. And all synonyms for one another. All right, sometimes the transformations do not preserve distance and angle measure because the pre-image and the image are not congruent. The ones that we'll be working with are called dilations, but there is another kind which is called a shear, and we're not going to be working with those. So a rigid transformation is reflection, rotation, translation, right? And those preserve our size, our shape, right? They ensure that our pre-image or image are going to be congruent to one another. So triangles are congruent if we can map one to another exactly using a sequence of transformations. And we have to apply that to each of our points. So let's add that too. I have one more thing for you to add. So you've added two things. Apply to each of the points. All right, so on the left-hand side, let's use my arrow. He was supposed to be pointing. He's not doing his job. All right, so here we went over rigid transformations. Of course, I wrote something down, so that helped you see where we were. And now we're going to look at this one, right? The diagram to the left, where we do have a transformation, a congruence transformation. All right, so notice our pre-image and our image. Of course, the pre-image is this one. It does not have prime marks on it, and then this one would be the image. And notice that each point moved the exact same direction, right? So they each moved to the right, and they each moved 2 spaces to the right. 1, 2. Each point went 2 spaces to the right. 1, 2, or 2 units. 1, 2. So what's a space? Unit's a little bit more specific. All right, so our rule is we have a translation. And I haven't written like this in your notes, but I usually like to make it the longhand that says the translation, x, y, is going to change each point using this rule, x plus 2y, right? So that means that our x coordinates are increased by 2, but the y isn't changed at all. So since we have the same rule for each point, our figures are congruent. I don't know what happened to that word. Looks a little funky, but that word is figures. You might want to make that clearer on yours if it's not clear. And so our congruence statement, whoops, hey arrow, is right over here. ABC is congruent to, triangle ABC is congruent to triangle A prime, B prime, C prime, right? We can say that because there's a rule that moves each point on the pre-image and maps it to the image. But let's look at the other diagram. All right, so let's look at A and A prime. All right, that moved 1 to the right. All right, so that rule would be translation, x plus 1, y. So every x coordinate increased by 1. The y coordinate didn't change at all. How about B? Well, here we have 1, 2, 3, 4. So the rule would be translation, x plus 4y. Each x coordinate increased by 4. The y didn't change at all. And then for C, we move 2 to the right. So the rule would be x plus 2, y. Right? So we have a translation, and we increased our x coordinates by 2, but didn't change the y. Well, do these look the same? X plus 1, x plus 4, and x plus 2? They're not the same. We have a different rule for each of our, not each point, not even just each point, each vertice here. Each of our our vertices of our triangle. So the figures are not congruent, right? There's not a single rule here. We have a different rule, right? So those are not congruent triangles, and we are not going to write a congruent statement because, well, they're not congruent. Can't write a congruent statement if your triangles aren't even congruent. And we're just waiting for the page to turn, and it's thinking hard, and here it is. This one's not in your notes. We're going to do a couple that aren't in your notes, and then we're going to do a couple in your notes. And it's transformations and congruence, right? So we're going to be graphing a couple figures and determining the rule, right, that proves, that maps our pre-image to the image, and that proves the two triangles are congruent. All right, so triangle PQR with vertices P4, 2, Q3, -3, and R5, -2 is a transformation of triangle JKL with vertices J, -2, 0, K, -3, -3, 5, -3, -5, and L, -1, -4. We're going to graph the original figure and its image, and then we'll identify the transformation and verify that it is a congruence transformation using the distance formula. So here we're using lots of stuff you've learned. We're using transformations. We're going to be writing a rule for that. And then we're going to be using the distance formula to show that all our sides are congruent. In a later lesson, you'll learn why that would actually prove your triangle's congruent. In this one, we're just going to be showing that the sides are congruent and defining the congruence transformation. All right, so let's graph our two triangles here. We have P is at 4, 2. And Q is at 3, -3. And R is at 5, -2. All right, and so there is our triangle. I probably should have moved P. I had to draw the triangle right on top of P. Can I get P out? I can mess up my old triangle. Here, we'll just get rid of it. There we go. Here, we'll write P above it. Oops, P above it. All right, and now let's graph the other triangle. J is at -2, 0. K is -3, -5. And L is at -1, -4. All right, so that one was J, this was K, this was L, and then we'll connect. We'll play connect the dots. All right, so now let's take a look. And so we can, by the statement here, right, so P is supposed to map to J. Right, so we gotta make sure we go the right direction. So P goes to J, and oh, excuse me. You know, just because PQR is first does not mean that would be the right direction, because PQR is the transformation. So J maps to P. Excuse me. And K maps to Q. I want to do it left to right, I guess. Oops. Well, if we move the arrow up slightly, yeah, it's pretty close. We know it's supposed to go right there. And then L maps to R. And there's L. All right, so now let's see how far each of our points moved. All right, so from J to P, we went 1, 2, 3, 4, 5, 6 to the right, and 2 up. And then K to Q, 1, 2, 3, 4, 5, 6 to the right, 2 up. And then L to R, 1, 2, 3, 4, 5, 6 to the right, and 1, 2 up. All right, so each one of these is the exact same transformation. It's a translation where each point is moving 6 to the right and is moving 2 up. All right, so now we're verifying, and so we're going to identify the translation, which we did, and then we'll use the distance formula to find the measures. You know, actually, in a later lesson, we'll be using the distance formula. So we are actually I'm going to end this sentence with identify the transformation and verify it's a congruent. We're just identify the transformation, and that's it. And we'll just verify congruence. All right, so I decided to shorten this a bit because I have other problems where we'll use the distance formula. So we're going to verify congruence, not using the distance formula, but instead using the definition. I have changed my mind. I can do that. It's my prerogative. We'll have enough when we do the distance formula. All right, so how do we know that these two triangles are congruent? Using the definition. Right? So since there is a sequence of rigid motions that maps triangle JKL to triangle PQR. Triangle JKL is congruent to triangle PQR, right? So we use the definition. And later on, we'll use the distance formula, and we're actually going to tie that into another way to prove triangles congruent. But right now, we're just going to be focusing on using transformations to prove congruence. All right, so here's this one. And then we're going to do this one as soon as it comes up. There we go. This one's already graphed. So we want to identify the transformation and verify whether it's a congruence transformation by mapping points. And we're also going to use the definition. All right, so we already have it mapped. We already have it graphed here. We know this one is the pre-image, right, because it doesn't have the prime marks on it. The green one is the image, right? So let's see how our points moved. All right, so it's facing the same direction, right? This has to be a translation. No change in orientation. Right, so orientation means the direction you're facing. Since the figures are facing the same direction, there's no change in orientation. For rotations and reflections, change the orientation. So the figures are facing the same direction. All right, so from P to P prime, I'll go 1, 2, 3, 4, 5, 6, 7, 8 to the right, and then 1, 2, 3, 4, 5 down. How about from Q to Q prime? 1, 2, 3, 4, 5, 6, 7, 8. and then 1, 2, 3, 4, 5. Exact same movement. All right, so I'm going to draw in the vectors actually. Otherwise, this is going to look like a bunch of polka dots. So we'll draw it in for P and Q, and then we'll finish off with R and S. All right, so P moved to, oops. All right, we'll kind of try and straighten it. There we go. P to P prime, right, was 8 to the right and 5 down. Q to Q prime was 8 to the right and 5 down. How about R and S? All right, so 1, 2, 3, 4, 5, 6, 7, 8 to the right, and 1, 2, 3, 4, 5. So R to R prime is 8 to the right, oops, and 5 down with a little glitch there. And then who's left? S. All right, 1, 2, 3, 4, 5, 6, 7, 8 to the right, and 1, 2, 3, 4, 5 down. Exact same movement. All right, so the rigid transformation. Sometimes I like to use different ways to explain things, right, so that you learn other vocabulary, other ways of saying things. You don't have to say everything always exact same way, but you have to have the key information. So the rigid transformation that maps P, Q, R, S to P prime, Q prime, R prime, S prime is a translation. Actually, let's just use the whole abbreviation. I was going to say it's a translation and then give the rule, but the rule includes the abbreviation for translation anyhow, which is the T. All right, so it's a translation where each point is moving 8 to the right and 5 down. There we go. Now we want to verify that we want to use the definition to verify congruence here. Right? So since there is a sequence of rigid motions that maps PQRS to P prime, Q prime, R prime, S prime. PQRS is congruent to P prime, Q prime, R prime, and S prime. And there we go. All right, so we've looked at some congruence transformations. I'm going to pause this video, and I'm going to meet you in the next video. And we're going to do a couple problems that are in your notes. All right, bye for now.